All right, folks. So we're going to get started with our procedural generation for crypto games workshop. This is a workshop on implementing Perlin noise in Solidity and some of the interesting techniques and tools that you can do there, as well as we're going to be contextualizing that in sort of a larger setting around where we think techniques for crypto gaming might be going. So again, by quick way of introductions for people who just cycled in, I'm Gubsheep. I'm the creator of Dark Forest, and I now work on ZK research and development with ZeroXPark. And I'm also going to be presenting this with Nalin, who has been building Excretia among a number of other interesting game and ZK experiments as well with ZeroXPark support. Okay, so first off, if you want to follow along with the code examples, and I'm actually not sure exactly how long we're going to have to get through all the code examples because we might have a stop at 30 or 45 after the hour, but we'll go through as much as we can. Prerequisites, node 16 or higher for using the demo repo, Yarn for dependency management. Ideally, you've written JavaScript and Solidity before. If not, you'll still be able to follow along with at least this presentation. And you'll want to clone nalin/devconnect-procgen-workshop, and then run yarn at the root of the project. So I'll give people 20, 30 seconds to do that and type that all in. So this is on GitHub also. So github.com/. All right, yeah, feel free to also slow me down if I'm moving too fast here. Okay, so before we dive into procedural generation, I want to make one thing very clear, and this has been a theme throughout kind of like this entire event, and it is that our goal is to build games. So there's been a lot of talk, especially in the last year or two, about crypto gaming, or even some people have started to appropriate a term from one of our other recent essays, crypto native gaming. A lot of the focus in the space, or the loudest voices on Twitter or wherever, are talking about things like, standardizing asset data models, or designing tokenomics and rewarding creators, and balancing staking rewards, and mobile wallet integration, or partnerships with AAA studios. I think that we got to get back to the basics here. There's pretty much no blockchain games outside of a small handful, many of which you've seen here today. And the thing that we need to do first is we need to figure out how to build a fun game on the blockchain. That's our goal. And the end goal of this workshop, the previous one with the ZK techniques, everything else is basically in service of that goal. The other stuff will get figured out later. So yeah, number one priority in crypto gaming should be how to make games more fun. And we think that things like procedural generation are a way to do that. Specifically, we're not focused on things like the financialization of everything, basically. I know especially right now there's been a lot of NFT speculation and hype. If you've been around for most of the day, one thing you might have noticed is that there's been very little mention of the words token or NFT. And that is somewhat deliberate. We're really trying to push the narrative on building out primitives and techniques that people can use to actually make games. So kind of one of the best case outcomes from workshops like this is that you go and you look at the starter repo and you use these techniques to basically build out something awesome. Okay, so let's contextualize blockchain gaming and some of these techniques. So my claim is that blockchain game development today is a lot like game development in the 90s on personal computers, consoles, etc. If we look back to 1990-ish and we look at consoles like the Game Boy, what we'll see is that we have these very rich and immersive games built for these extremely resource-constrained environments. So the Game Boy, which I believe was released in 1989, initially only had 64 kilobytes of memory, which is insane today. When I open up my activity monitor while I'm playing a game or something and I look at the memory usage, I'm it's just orders of magnitudes off. But I think for anyone who has programmed in Solidity before, you've probably also encountered a bunch of weird constraints and bugs and things stack too deep. I've still just never really been able to wrap my head around exactly when I'm going to and not going to get stacked too deep. Or like this caused us a lot of pain in the early days and is actually like, kind of like funnily reminiscent of what was going on here. I remember running into the smart contract size limit for the first time of 24 kilobytes. And obviously it's not exactly analogous because, the sort of like resource dimensions are different and you can do different things like the diamond pattern or whatever else. But just noting that like we're talking about kilobytes here. We're not talking about like, tens or even hundreds of megabytes that we have to work with to try to build these like rich and immersive experiences. So like the indie game devs of the 90s, we're going to have to hack, golf, and get clever. If you've ever read any stories or like about kind of a lot of the techniques that people were doing back in the early days of gaming, I'm always really inspired to see all the really interesting things that like people were doing to just hack more content or sort of more like better graphics or whatever else into games. And I know some folks here who have been around the industry for a very long time probably also have memories of this kind of like way of working, and I think that this is something that we're going to have to bring back. Okay, so let's talk about procedural generation. Procedural generation is basically a set of techniques for generating rich and immersive worlds algorithmically. So in other words, rather than needing like a map maker or level designer to place down every single tile individually, what you can do is you can define a mathematical function that basically tells you at any given square what should the tile at that square be. Should it be grass? Should it be wood? Should it be tree, water, etc.? And one of the cool things about procedural generation is that it allows you to save on all sorts of resource costs. You can effectively have infinite content, quote unquote, for simply a constant sized mathematical function. You don't need to store in memory what everything is at every square. So these screenshots are examples from like Minecraft and No Man's Sky, which are particularly good modern examples of these techniques leveraged really well. But if we go back to even like the 80s and games like Rogue, you can sort of see that initially these techniques were largely invented to give game devs a little bit more breathing room to work with more content and just like having a wider level variety or diversity or things like that. So this game, Rogue, which inspired the roguelike genre of dungeon crawlers, you can see it's ultra simple. You're playing with basically just like a grid of ASCII characters. But one of the really amazing things about Rogue for its time was that it was the first game to actually demonstrate procedurally generated levels, which meant that the game could use less memory and players could get more bang for their buck essentially out of playing these games. Similarly, in a lot of the games in the 0x Park community today and adjacent communities, procedural generation tools are just starting to get experimented with to create more interesting worlds. So this is a screenshot from a build of Dark Forest that's about 15 months old or so by now. One of the first times we had procedural generation entered into the game in order to create new multiple different types of space types and biomes. So now you have deep space and you have nebula and you have like the lava planet biomes and stuff like that, and each of these has different properties. This is using similar techniques. Ember, which is the prototype game being built on Lattice currently by a lot of the Lattice team, also uses this very same implementation, in fact, of Perlin noise that's used by Dark Forest to generate where different resource hubs are located on the map. And Xgratio, which we saw earlier today as well, you can kind of see that, this map to me suggests very much an RPG style of on-chain game. You've got like the frozen wastelands to the north and like the deserts to the south and some sort of like fertile, more friendly like foresty kinds of biomes through the middle, and you've got like land and sea and water and all this stuff. And basically, unlike I know that there have been historically a couple of experiments in Ethereum around like building R/place style things where you start off with like a really big blank white canvas and people just put stuff on it. Our sort of thinking is that these techniques are really powerful because you get to start with a world that has some interestingness or depth to it rather than just like a blank slate and try to bootstrap everything off of that. This is a tool that helps your world feel more real. Yeah, so why is this useful specifically in terms of technical details? Storage on chain is really expensive. If you want to store 1,000 by 1,000 like tile map of you into 8s, that's probably going to look something like hundreds of millions of gas. And rather than storing a whole world on chain, we can just store a single function. So we have the compute Perlin function here, which like executes some code. I think it's something like 100K gas per call, and you effectively get an infinitely large map. So the particular algorithm that we're going to dive into today is called Perlin noise. And what Perlin noise allows us to do is essentially we can use it to generate a terrain map. In other words, we have this like, we can generate these like terrains that are locally smooth but globally random, i.e. if something is a hill or if something is like the top of a hill, then the points close to it are also going to have like a high terrain. If something is a valley, then the points near it are also going to have a low altitude. But overall, if you look across the whole terrain, there's going to be a huge diversity of different altitudes and features. The high-level strategy for Perlin noise, to get into the mathematical details, which we're not going to do in code today, but for those who are interested, is when we look at a terrain and we divide it up into little like grid cells, each of these grid cells essentially has some slope that's going to define how steep up or down your traversal of the terrain at that grid point would be. And what we're going to start from is we're going to choose terrain gradients randomly at grid corners when we're trying to generate a new terrain, i.e. we're going to pick these slopes first. And then what we're going to do is we're going to interpolate, i.e. we're going to fit a particular set of altitudes onto this map such that the overall terrain has the slopes that we've chosen at each of those grid points. So here you can see a simple example where we've created like green is mountains, purple is valleys, and all of this is in accordance with the various gradient points. Okay, so let's get to some code. All right, so what you're going to want to do is you're going to want to check out the branch checkpoint1 start and run yarn at the root of the project to install dependencies. And we're going to start working with just some like very simple terrains here. While people are doing that, I'm just going to give a little bit more insight into what is going on under the hood. So at the core of everything that we're doing today is going to be this function Perlin that takes in two inputs. The first input is a pair of x, y coordinates, and the second input is a set of options, things like, how bumpy do you want the terrain to be? How, like, you can swap out different seeds and like regenerate worlds. You can set a scale, which is like the scale of world features. Should this landscape be very stretched out or very, very packed tightly? And we're basically going to be using this very simple building block, this Perlin function, to compose into a variety of different on-chain worlds that one can interact with. Okay, so let's just run our demo at the starting state. And what we have as the starting state is a very simple heat map, essentially, of the like a single dimensional Perlin function over a 100 by 100 grid. So you can see that it looks a lot like this heat map over here. Now, this is obviously a very far cry from our goal, which is this, or even further, something like this or this, right? But it is a basic building block, and we're going to look at a couple techniques from getting from here to here. This is our goal. By the end of the workshop, or if you go through and sort of can build out everything, then you're going to end up with basically like arbitrary biomes, land, water, different types of tiles, all this stuff. So the first thing that we're going to do is this thing that we have generated here looks really like rough around the edges. It's somehow not very smooth, and this is a consequence of what we're using as the interpolation function, which is something that unfortunately does have to be EVM friendly. Has like these sort of weird-ish, jaggedy kinds of lines going on. Interpreted as a terrain map, this is like sort of weird, in short. So the first thing that we're going to do is we're going to add multiple octaves. In other words, I'm going to go to the code example here. And I'm going to play around with a few of these constants. So first off, you can see that there's this constant world scale, which is currently set at 8 tiles, meaning that like every 8 tiles, we sort of generate a new gradient vector. So what happens when I set this to 16? You know, I'm going to double it. Okay, so now what you can see is that like this world is a lot smoother. The world has sort of been blown up like a balloon. If I change this value to 32, so every 32 tiles I see a gradient shift, then what I'm going to get is an even larger and smoother length scale. But now I have a different problem, which is that like this grid is almost too smooth. There's like not enough going on. Like I like the fact that overall this is like a mountain and this is a valley, but one thing that would be cool is if there was a little bit more local variation. That's one thing that's going to help us to get this greater levels of realism that we see in interesting games. So in order to do that, what I'm basically going to do is I'm actually going to set my Perlin function to be a weighted average of single octave Perlin functions at different length scales. So the way that I'm going to do that is I'm going to go into my implementation of perlin.ts. So if you're following along on like VS Code, you can go Control-P, perlin.ts to find this file. Scroll to the bottom. I'm going to set octave 1 to equal the current value. I'm going to set octave 2 to be like the value of this with a scale twice as large. And then I'm going to set octave 3 to be this value with the scale 4 times as large. And then what I'm going to do is I'm going to return some weighted average of these 3. And one kind of nice default that you can imagine is like every time the length scale doubles, the impact of that octave is going to double as well. So I'm going to do return 4 times octave 3 plus 2 times octave 2 plus octave 1 divided by 7. And then here I'm actually going to have to rerun yarn because this is in a package. So if you're following along after you make that modification, go to the top level and type yarn, and that will sort of like refresh the Perlin function. Okay, so now let's see what we have. Oh, I forgot to also change the, no, the world scale is still 8. Cool, so let's see what we have now. Nice, okay, so this looks a little bit more realistic. Now we have like these areas that are, this area as a whole is globally higher up than this area as a whole. But within this area, we have a little bit more local variation. So we've achieved this nicer balance between smoothness and sort of like local interesting features. All right, so we've made our heat map a little bit more smooth, but one of the problems is that this is still a heat map. And what we'd like to get to is rather than this fuzzy cloud kind of looking thing, we want to get to a map that has tiles and an algorithm that knows how to generate tiles from this heat map. So what we're going to do is we are going to define a mapping essentially from values on this heat map to actual tile types. Sorry, let me look in my notes real quick. Okay, so currently the way that the background color of each of these squares is set is that we just take the computed Perlin value and then we map that onto a grayscale spectrum. And instead what we're going to do is we're going to compute a tile type from the Perlin value, and we're instead going to display the color of that tile type. So let's start off with just something really simple. We're going to say half the tiles are land. Those are the ones with altitude greater than 0. Half the tiles are, the altitude scale is actually 16 to 48. Half the tiles are land. Those are the tiles that are at least height 38. Half the tiles are water. That's the tiles with height less than 32. So we'll say if Perlin greater than or equal to 32, return tile type dot grass. Otherwise, we're going to return tile type dot water. Okay. And you can alter this seed to tile type function in utils.ts. So for those of you who are following along, just like implement this function to have whatever thresholding you want. And then in the game, we're going to go tile type, and we're going to display the appropriate color of the tile type. So we're going to say tile type to color. Okay. Oh. Let me see if I got something mixed up here. Here we go. Okay, cool. All right, so now you can see that we've got this world that's got land and water. It's got global structure and some local variations, so we're definitely getting somewhere that's like a little bit more realistic. So the next thing that we can do is actually we can start to add more layers in. We can make it so that instead of just land and water, we can also have beaches and mountains. So maybe beaches are things that are kind of on the edge of water. Mountains are things where it's like if you go really high up, then if you go to really high altitudes, then you'll have like mountain tiles. So let's go into utils, and we're just going to add to this seed to tile type function. Maybe above 40, we're going to have like snowy mountaintops. So we might say return tile type dot snow. And if we're above altitude like 37, then we're going to be on the mountain, so we'll return a stone tile type. And then grass and water sort of as we would expect. Actually, we want to also do beaches. So maybe we'll make this like 34. And we'll make this 32 as sand. So the other thing that I'll note here, and this is sort of setting up for Nolan's section, is that the particular implementation of this Perlin function that we have here has specifically been made to be Solidity and Snark friendly, meaning that you can take this and you can basically mirror this into a parallel implementation on your Solidity smart contract, or you can even put this inside of a Snark if for whatever reason you need to keep tile information private. So what we're going to do next after we play around with building out this world is we're going to see what it looks like to have a parallel implementation and be able to link those two things together. So here's my map. As you can see, we've got these beaches that sort of define the border between land and water. Then I've got these grass types. I've got a couple of hills, mountains. This mountain has a really big snowy top. I kind of want it to be that mountaintops are a little bit more rare than this. So maybe what I'll do is I'll go in and I'll set the threshold here to be a little bit more aggressive. And this is the kind of example, this is an example of the kind of thing that you can do once you have these starter kits and the way that you might go about basically playing with different procedurally generated landscapes. You can basically you've got this set of constants, you've got this set of tiles, you can play around and see what you like, what you don't like. Okay, cool, so this is a little better. Now we don't have so much of this snowy mountaintops everywhere. It's only this one really big mountain on the right side. Yeah, so we can do things like play around with different thresholds, different length scales. We sort of demonstrated that. As one final thing before I turn it over to Nolan, I'll show what happens if we sort of just refresh the seed. So right now the world seed is just 0. Let's set it to 1 and see what we get. Cool. Totally different map, but with the same kind of general parameters. Here we've got 2 of these snowy mountaintops and a really big ocean to the top left, only with a couple of islands in it. But you can kind of see that structurally this is very spiritually similar to what we previously had. Question? Yeah. Yeah, exactly. So this is where we can start basically remixing a bunch of different ideas. And this is actually what Nolan is going to show as well. You can, like the way that Dark Forest does this is that it has two independent Perlin noise functions. And so you can imagine basically like, you know, and it has like thresholds for 3 different like classes. And between these two functions, you have like 9 possible combinations of where you sit on the total threshold graph. You can also mix in things like just pure RNG, where you're like, okay, forest biomes have a 25% chance of spawning trees in any given tile. And there's all sorts of like little tricks that you can do. A lot of this is like very ad hoc also. It's not like, you know, there's necessarily like a standard manual of techniques. You just sort of, it's almost empirical. You just like tune stuff, come up with an interesting idea, and then just roll with it. Does that answer the question? Oh yeah, and also for the recording, for folks who couldn't hear, the question was basically, can you mix multiple Perlin noise or RNG functions together? All right, so with that, I'll turn it over to Nolan, who will link up this work to the Solidity side and also demonstrate this like multiple octave thing. Maybe one more thing that I'll just mention here is like, we are like very excited for people to try to build stuff with this primitive. It's actually like kind of shocking to me that like no one has so far, because, you know, this isn't something that like needs snarks or anything. And in a really computationally constrained environment, this feels like one of the first things, one of the first kind of like techniques from the toolbox of hacks and tricks. So an on-chain like RPG or like management sim or anything like that would just be like very awesome and has the potential for, you know, being an MMO because everybody's on the same global shared state. You can obviously have all your like item stuff, sword, NFTs, whatever else. But all right, Nolan, do you want to come up?
Nice. Yeah, so I'm Nolan, and I will pick off of where Brian left. So workshop part 2. So I guess the goal now is to start with something more like this, which is just water, just land, and we now want to do something more sort of fun to it, right? So one thing you'll notice here is that this landscape is actually slightly more, let me also turn this off, slightly more complex than what Brian had. Like there is a lot more going on if you look at like the number of different island structures and things like that. So the reason for that is that we are actually using 2 Solidity or 2 Perlin functions here instead of just 1. So it is sort of like the idea of having multi-octave, but now you have multi-dimensions. I think one way to think of this is just like you have like sine functions and you're just like combining 2 sine functions and taking like sum or something of, or average or something of those. So it is like you're increasing the complexity of like the wave form you get. Yeah, that's how you can get more complex sort of islands or crazy structures. So for this, you should start with the branch part 2-0. And if you look in this branch, let me increase the font size. Okay, so in this branch, you'll see that we have this Perlin config that actually you can play around with a lot, right? So the Perlin config allows you to edit the seed, the scale, and there's some other parameters which we won't talk too much about. But so for one, the scale is just like a value of like, oh, also I guess if you think of scale as like a sine function kind of thing, it is like how stretchy or how small your sine wave looks like. So scale is something you can also play around with. So for instance, let me actually go and try to change this C to be, let's say 64. So right now it's 42. And we will see a completely different set of islands. Hopefully. Yeah. So So that is sort of how you add in more complexity to your structures that you have. So if you jump to branch part 2-2, wait, okay. So this is the branch where things get really more interesting, and you start to see structures more like ex gratia. Oh, zoom in. Oh, can I just do this? Okay. Yeah, so this is where things start to get really a lot more interesting than before, and you start to see structures that are sort of resembling of ex gratia. So one feature that was really visible in ex gratia was, that Brian also talked about, was this ice realm, right? So you see how there is this some sense of pattern where there is a sand or like a beach area towards the bottom, and then there's a grassy area in the middle, and then there's more ice to the top. So that is sort of one of the features you would like to have, right? Like you would want some amount of pattern, and that's how real world works. So you want patterns like this. So one question is like, how can you encode these patterns using Perlin? So one of the ideas is that you can literally change the function of the output of Perlin to be such that it has some sense of this pattern. So the way we can do that in case of our code is that we can literally take temperature of a place to be a Perlin value, and then instead of using the Perlin value as is, we can force it to be dependent on the x coordinate of this location. So whatever is at the top, by default gets weighted down. Whatever is at the bottom, by default gets weighted up. And so now you have, even though it's like a ridgy, wavy function, you have this pull down and pull up effects. And at the end, you have like some sense of pattern along with some complications of like, oh, now there is a pattern to the, like there's mountaintops in between, but also there's ice realm at the top. Yeah, so that is, I guess, one of the ideas of using, as Uma was asking earlier, sort of Perlin along with other RNG and other environmental factors. Yeah, and I guess the function that decides what the output of your tile type is also is a lot more complicated than before. So Brian was working with one of these Perlin values and had something pretty similar to the first like line 24 to line 32. But now that we have the intuition for temperature, so Brian basically had altitude built in, right? Because Brian had mountaintops, mountains, land, and sea. And now with the addition of temperature, we can add in like, oh, this tile is cold and this tile is hot. So a hot mountaintop looks different than a hot, I don't know, like hot sand area or something. So you can combine all these things to create, as Brian was describing, Dark Forest has this 3x3 of the Perlin. You have a 3x3 or n×n from Perlin values, along with patterns in one of them while not having any pattern to the other one. And I guess one other cool thing is that you can literally edit these values yourself and see different results. And for instance, one thing you could do is like literally change the output of these colors to represent things like the nether region in Minecraft. Or so, for instance, this water could then be lava, or the I don't know, the sea could be some moon water or something. So you can do all sorts of crazy changes just to these color schemes right here and get all cool landscapes that you want to make. Yeah, I think that's mostly it. Okay, yeah, that's it. Thank you.
One other thing that I'll note is that there are reference implementations of all these things in the repos that we've linked here. And there's Solidity implementations as well as JavaScript implementations, and the same thing for the tile type function. The other thing is, one more note also is that you can find reference implementations for this kind of stuff inside of a snark in the Dark Forest open source repo as well. Question?
I was just going to ask about Snark, actually. Like, just briefly, when you said it's Snark compatible, noticing, what did you mean by Snark
Yeah, so basically, the only thing that you can do in snarks, as we mentioned in the last workshop, is you can only make proofs about plus and times operations. So Perlin noise, typically, you're going to use things like sine or other trigonometric functions. These don't really fit very nicely into plus and times. So we use like a number of different hacks to make it so that you only have to work with very, very basic arithmetic operations to get something that still looks pretty decent. Question? The use case for in dark forest for what? What's the dark forest use case for Perlin noise in the snark? Yeah, so the question is, what's the use case for dark forest Perlin noise inside the snark? The thing that you need to be able to do whenever you're interacting with a planet is you need to be able to prove to the smart contract all of the properties of that planet. So you need to be able to tell the smart contract, like, this planet is in nebula, and planets in nebula have an automatic, like 50% debuff on this stat. So normally, the way that you would compute what region something is in is you would pass the coordinates, like x comma y, directly into the function. But here we're trying to keep x comma y secret. So not only do we have to make a zero-knowledge proof about the location of the planet x comma y, but we also have to include a proof that that secret x comma y, when run through the procedural generation function, results in a particular kind of, results in the planet being in nebula, and therefore it should automatically be assumed to have a 50% debuff. Yeah. Yeah, so the question is, why can't we just use like the hashes of the planets, because those are those can be like basically treated as randomness. The answer is we do. In fact, like planet levels and various different buffs and other properties are indeed computed from the planet hash. In addition, the thing that Perlin noise adds, though, is that you can have like, if you just have pure randomness and you like zoom out, then the universe just looks like pure noise. It's just like every point is completely random. But what Perlin noise allows you to do is it allows you to have this locally smooth but globally random property where planets that are close to each other have similar properties. So we can say that this region of space is a nebula. And making your way through nebula is difficult for these particular reasons. Maybe you want to go from nebula to deep space because deep space is where all the good resources are. And the experience of playing the game is basically traversing as an explorer through all of these different regions and biomes until you get to the place with the best artifacts or the best silver production or stuff like that. Any other questions? Awesome. All right. Thanks everyone for coming.